Hi everyone. In this video we discuss the formal definition of a group. Informally, a group G, star is a set G possessing a well-behaved binary operation star. Now, eventually we're going to have to come to terms with what we mean when we say well-behaved. But for now, maybe it's enough to say that whatever well-behaved means, it should imply that equations of the form A star x equals B have unique solutions in G for each choice of specific elements A and B in G. So the question in front of us is, well, what properties must this operation have in order to force these unique solutions? So to try and discover what those properties should be, maybe what we should do is work an example in a familiar setting. So here we have this equation, x plus 3 equals 5, and we want to solve this equation in the integers. And the operation that we're using is addition. So we know that the answer is 2. But let's suppose we didn't know that and we wanted to solve the equation. Well, how would we do it? Well, the first thing we would probably want to do is get rid of the 3 on the left side. And so I start with my x plus 3, and the thing that I would want to add would be minus 3 on the left. And whatever I do on the left, I need to do on the right, so I go ahead and do that. Add minus 3 on the right. Okay, now we know that the 3 and the minus 3 together give us 0. But really, in order to see that, we first need to regroup the addition. Right? We need the 3 and the minus 3 to be together. So let's do that. And now over here, because addition is a binary operation on the integers, I know that 5 plus minus 3 is again an integer, and it turns out to be 2. All right. So now where from here? Well, the reason why we added minus 3 to begin with on the left side was so that we could take 3 and add it to minus 3 and get 0. So 3 plus minus 3 is 0. And on the right, we still have 2. And now we're almost done. And the thing that we need to observe is that 0 is an identity in the integers. That is, if I take x plus 0, that's exactly the same thing as x. And so there we are at our solution, x equals 2. And now we should sort of keep track of the things that we needed to do in order to solve this equation. So the first thing that we did is we did some regrouping. In this step right here, we did some regrouping, and that means that we applied the associative property. So the associative property got applied. And we also used the fact that addition is a binary operation on the integers, and that means that when we take 5 plus minus 3, we're bound to wind up with another integer. In this case, we wound up with 2. So we used the fact that addition is a binary operation. Now, in the next step here, we made use of the fact that 3 plus minus 3 is equal to 0. And that's sort of an inverse property, right? Where if you take a number like 3, then there's some other integer like minus 3 that you can add to it to get 0. So we sort of applied an inverse property there. And then to get down to the last step, we used the fact that 0 is an identity, meaning that when we take any number and add 0 to it, it leaves that number unchanged. So in this whole process, there were sort of four things that happened. We used the fact that the operation is binary. We used a grouping property, which we call associativity. We used an inverse property, and we used an identity property. Now we're ready to see the formal definition of a group. So a group, G comma star, is a set, G, together with a binary operation star, possessing three properties. The first property is that we require the operation to be associative, which, as you'll recall, means that regrouping does not affect the outcome of an operation. The second property is an identity property. It's asserting that there's a special element, E, lying in G, such that when we apply E to X, either on the left or on the right, it leaves X unchanged. And that's going to be true for any X whatsoever in our group G. And then finally, we have an inverse property. So if someone hands me an element X in G, then I must be able to find an element Y in G so that when I apply X to Y, either on the right or on the left, I wind up with this special identity element. So the special element E is called the identity, as we've been saying. And if we're given X and we find this special Y such that X star Y and Y star X are both equal to E, then we call Y an inverse for X. And then in the example, we saw that it's important that this operation be binary. All right, now occasionally we have the additional desirable property that the order in which we multiply things doesn't change the outcome of the calculation. In other words, sometimes it's true that A star B equals B star A for every A and B in our group. And when that special thing happens, we say that our group is abelian. So abelian, that name comes from the name of Niels Abel, who was a 19th century mathematician. He was one of the first people to prove some results about the insolvability of quintic equations. Okay, there are many, many examples of groups, ranging from examples that we've been familiar with for a long time through examples that we're just encountering now for the first time. So in our first bullet point here, we have some examples that I'm sure all of you are familiar with. If you think about the integers with the binary operation of addition, that is a group, as is the rational numbers under addition, the real numbers under addition, and the complex numbers under addition. All of them are groups. Similarly, there are multiplicative groups. So the non-zero rational numbers under ordinary multiplication form a group, as do the non-zero real numbers and the non-zero complex numbers. You might notice that the non-zero integers under multiplication is not listed here, and you might be thinking or asking yourself why it's not listed there. If you're asking yourself that, then that's a good question. Okay, on to the next example here. We can think about M as being the set of all 2 by 2 matrices with integer entries, and if you let plus be matrix addition, then M comma plus is a group. And in this group, the identity would just be the zero matrix, where all the entries are zeros. Now there's a multiplicative matrix group, M bar comma dot, where M bar is the set of all invertible 2 by 2 matrices, and the dot represents matrix multiplication. So there, the identity of the group is what we call the identity matrix, which you may recall from linear algebra. So that's this matrix here. That's the identity in that group. And then in your reading, you've encountered this group, P of S, comma, triangle, where this P of S is the power set of a given set S, and the triangle represents the symmetric difference operation. So that turns out to be a group, and the identity there is the empty set. And then finally, you saw a video about symmetries of the triangle. In fact, if you look at the symmetries of the like an equilateral triangle, that forms a group where the operation is just composition of symmetries, and the identity in that group is just the symmetry that does nothing. It just leaves the triangle where it is without doing anything. Now we have a list of sets with binary operations that fail to be groups. This might be a good time for you to pause your video and look at these examples and see if you can determine why these are not groups. Okay, I'm assuming now that you've paused the video and thought about it for a little bit. So we want to show that each of these sets with a binary operation fails to be a group. So we begin with the integers under ordinary multiplication. Now, if this were to be a group, we would want the identity element to be equal to 1, right? Because anything times 1 equals itself. But if that's the identity, it doesn't take long to find an integer that fails to have a multiplicative inverse. For instance, the number 2 has no multiplicative inverse in the integers. Right, it's a multiplicative inverse. We want it to be 1/2, right? But 1/2 fails to be an integer. And therefore, the integers under ordinary multiplication fails to be a group. Okay, our next example is the integers under subtraction. And you may recall that earlier, when we were discussing subtraction, we discovered that it fails to be associative as an operation. But associativity is something that is required for a group. Therefore, the integers under subtraction fails to be a group. Next, we have this set O of odd integers under addition. This fails to be a group for a variety of reasons. The first is that there's no identity that lives within this set of odd integers. You would want the identity to be 0, but 0 isn't odd, so it doesn't live within the set of odd integers. The second thing is that addition isn't even binary on the odd integers. For instance, if I take 1 plus 3, both of those are odd integers. When I add them together, I get 4, which is something that's not odd. Okay, moving on to the next example, we have this entire collection M of 2 by 2 matrices with real entries under matrix multiplication. Now here, if there were going to be an identity, it would have to be the identity matrix 1, 0, 0, 1. And this almost works, except that there are some matrices, like for instance this one, A equaling 0, 1, 0, 0. That thing has no inverse. It's not an invertible matrix. So if you're going to make this into a group, you need to restrict yourself to the collection of invertible matrices. And when you do that, you do obtain a group under matrix multiplication. Okay, moving on to even more obscure things. We were talking earlier about the power set being a group under the operation of symmetric difference. And you might be thinking to yourself, well, why do we have to have an operation that's as complicated as symmetric difference? Why couldn't we use an operation that we're familiar with on sets like intersection or union? So here we're going to consider the power set of 0, 1, 2. Now remember, the power set just consists of this set and all of its subsets, and the operation is going to be intersection. So here, if this were going to be a group, then if you think about it for a little bit, the identity element would have to be this entire set, 0, 1, 2. And if that's the case, then there are a variety of sets that will not have inverses. For instance, the set 0, 1, right? There's nothing you can intersect that set with in order to obtain a larger set like 0, 1, 2. So this has no inverse. Okay, well, intersection didn't work. What about union? Well, under union, the identity would be the empty set, right? If you take any set and you take its union with the empty set, you just get that set back again. So the identity would be the empty set. But then, as in the previous example, lots of other sets, like for instance 0, 1, again, this is not going to have any inverse because there's nothing I can union with 0, 1 to obtain the empty set. So this has no inverse. Our next task is to discuss the group of modular integers. This is an arithmetic on a finite set. You may or may not have seen this arithmetic before. The modular integers z sub n consists of the numbers 0, 1 through n minus 1. So here we require that n be a fixed positive integer. So now we have this set of n integers, and we're going to define an operation on it in this way. So if I take two of these integers, I'm going to add them together, and then I'm going to compute the remainder that I obtain when I divide the sum by n. So that's our operation, right? You take two numbers, you add them together, and then you compute the remainder when you divide by n. So it turns out that this set that we call z sub n, paired with this binary operation, is an abelian group. And we call it the group of integers modulo n under addition. Now for a specific example, we can look at, say, z5. And here we have an operation table for z5. Now how does it work? Well, let's suppose I want to know what 2 plus 4 is in z5. Well, I can find 2 in my first column, and I can find 4 in my first row. And if I want to know 2 plus 4, where I'm adding in z5, I just find the entry that's in the same row as 2 and in the same column as 4. Turns out it's equal to 1. Now let's just make sure that that makes sense, right? So if I take 2 plus 4, that gives me 6. When I divide 6 by my modulus, which in this case is 5, if I take 6 and divide by 5, I'm left with a remainder of 1. So indeed, that does work. We can gain greater familiarity with the definition, the formal definition of a group, by verifying that the modular integers is indeed a group. Now, to do that, we need to start with a few facts, or a couple of facts about the integers. The first fact is this division algorithm, which is probably familiar to you. So if I take two integers, a and n, where n is a positive integer, we know that we can divide a by n to obtain a unique quotient q and remainder r, where r is strictly less than n and bigger than or equal to 0. So the division algorithm implies this corollary, which says that if you have integers a, b, and n where n is positive, and if a bar and b bar are the remainders that you get upon dividing a and b by n using the division algorithm, then a bar equals b bar, that is, the two remainders are equal if and only if the original numbers differ by some multiple of n. So we now verify that the modular integers under this new addition operation, circle plus, is a group. And in fact, we'll show that it's an abelian group. Now you might remember from the formal definition of a group that there are essentially 4 things that we need to check. The first is we need to know that this operation, this circle plus, is a binary operation. And then, once we know that, we need to know that there's an identity element in our group. We need to know that each element in the group has an inverse. And then finally, we need to know that the operation is associative. Now, since we're to show that this is an abelian group, we will also want to show that the operation is commutative. Now remember, I haven't written it on this slide, but I want you to remember that this operation circle plus, it's essentially ordinary addition, but then we compute a remainder modulo n. So that is important to keep in mind here. So the first thing we're going to do right in this step is check that the operation is binary, right? Well, if I take two elements, a and b, in Zn, and then I add them together and take their remainder upon division by n, I again get a number that's between, that's 0, 1, 2, up through something up through n minus 1, right? Those are the possible remainders upon division by n. So this new thing, this a circle plus b, is again lying in Z sub n. So that means that it's a binary operation, and furthermore it's commutative because, essentially because ordinary addition on the integers is commutative. Okay, now in the next step, we're checking about the identity. Well, the obvious candidate, I think, for an identity here would be just 0. And indeed, if we take a circle plus 0, we wind up with a for each a in Zn. And likewise, 0 circle plus a is equal to a for each a in Zn. And so 0 is the identity that we seek. And in the next step, we're looking for inverses. And there are 2 cases, essentially, to check. So first of all, let's suppose we start with an element in Zn that's non-zero. Then if we take n minus that element, that, again, is going to be something in Z sub n. And if you add them together in Z sub n, like here, what you wind up with is 0, which is exactly what we wanted. Now, on the other hand, we need to see what happens when we consider the 0 element. Well, the 0 element is its own inverse. If I take 0 plus 0, I wind up with 0. Therefore, we have now considered every element in Zn, both non-zero elements and the 0 element, and every single one of them has an inverse in Z sub n. And finally, and this is probably the most complicated of the verifications, is showing that the operation is associative. So here we begin with a, b, and c in Z sub n, and we take a plus the quantity b plus c. And we want to ultimately show that that's the same as the quantity a plus b plus c. And luckily, we are able to get from one to the other through a chain of equations. So what we do first is just sort of unwrap the definitions, right? So here we're just applying the definition of circle plus. And again, here we're applying the definition of circle plus. Now, to get to this next step right here, to get to this step right there, what we need to do is know that the two quantities that are underneath the long overbars differ by a multiple of n. And indeed they do. If you subtract those two quantities under the long overbar, you'll get b plus c minus the bar of b plus c. And that's essentially the difference between a number and its remainder upon division by n. When you take that difference, you will wind up exactly with a multiple of n. And remember earlier we said that the overbar, or the remainder, of two numbers is identical exactly when the numbers differ by some multiple of n. So anyway, next we apply the associativity of ordinary addition on the integers to get to this next step. And then we reverse the thing that we did a little while ago. Again, here in this step that I'm now marking, what we need to know is that the two quantities under the long overbars are different by a multiple of n, and indeed they are. And then in the final steps, we are, again, unwrapping definitions, right? A plus b with an overbar is just a circle plus b. And then this last overbar becomes another circle plus, and we wind up exactly with what we wanted. We finished the video with an example of a group that I consider to be pretty interesting because almost everything about it seems unfamiliar. We begin with this set consisting of the positive real numbers except 1. So it's every positive real number you can think of except for 1. And we're going to pair that set with an operation star where to take a star b, we just take a and we raise it to the logarithm of b, where the logarithm is going to be base 10. So the first thing that we need to know, if we're going to show this as a group, is that this operation is binary on the set. And in fact, this r plus here should really be an r plus minus 1. So we want to show that that's a binary operation. And indeed it is, because if a and b are two positive real numbers that are not equal to 1, and you take a to the log b, again you will get a number that is a positive real number that's not equal to 1. If that's not immediately apparent, then you might think about that for a little bit. So we've handled the binary aspect of the operation. Next, we address the associativity of the operation, where we start with a star the quantity b star c, and we want to show that that's exactly the same as the quantity a star b starred with c. Luckily, we can get from the one to the other through a chain of equations, and as we proceed through this chain of equations, we're going to need to apply a property of logarithms together with a property of exponents. So in the first two steps, we're not doing really very much. We are just unwrapping what's meant by the star operation. And then finally, in this third step, we're applying a property of logarithms that says if you take the logarithm of b to some power, then you can bring the power out in front of the logarithm. Now, in going from this step to this step, we're really not doing anything except applying the commutativity of multiplication of real numbers. Now, in this next step, we're applying a property of exponents. If you take a to the m times n, that's the same as a to the m to the n. But now we recognize a to the log b as being a star b. And then anything to the log c is that something starred with c. And that takes us to the end of our chain of equations. And that tells us that the operation is associative. Next, we address the issue of identity. Well, if we're going to have an identity in this group, we need to have that a to the log e equals a, and e to the log a is equal to a. And for those equations to hold true, we need e to be equal to 10. So 10 is the identity in this group. That seems rather strange, but that is the case here in this particular group. Okay, we carry on with the example that we began on the previous slide. On the previous slide, we introduced this set with this binary operation, and we showed that the operation was binary and associative, and we also identified an identity element for this group. And now it remains to show that each element in this set has a multiplicative inverse. And we'll also show that the operation is commutative in order to show that this is, in fact, an abelian group. Okay, so we'll address inverses first. So we start with some positive real number that's other than 1. And we're going to let y be this number, 10 to the 1 over log x. Now, here for the first time, we see why we want to exclude 1 from this set. If x were equal to 1, then the log of x would be 0, and in the exponent of y here, the 1 over log x, we would be taking 10 to the 1 over 0. So division by 0 is a bad thing, and therefore it's important that we exclude 1 from our set. Okay, so anyway, we're given a set x, and I'm proposing to you that this, we're given this element x, rather, that's a positive real number other than 1, and I'm proposing to you that this strange-looking y is an inverse for x in this group. So I've given you two equations, or two chains of equations to consider. Probably this bottom one is the simplest to consider first, right? If we take y times x, that is 10 to the 1 over log x to the log x. And then by multiplying exponents, we see that that's just 10 to the 1. But remember, 10 was our identity. So when we take y star x, we get the identity. Now, a few more steps are required to show the other equation holds, right? So now if we take x star y, we go through, we apply some properties of exponents and logarithms to eventually obtain that a result of 10, which again is the identity. So this y is in fact the inverse of a given x. Okay, and now finally, let's check that the operation is commutative. So if we take two elements x and y in our set, we multiply them together, which we recall means that we take x to the log y. X can be written as 10 to the log x by properties of logarithms. And now we multiply, we apply this property of exponents to say that that's really the same as 10 to the log y to the log x. But that's just y to the log x, which is y star x. And hence, x star y and y star x are the same. And we conclude overall that this set with this operation is an abelian group.